We've spent 4,000 years building the world like stone carvers, chipping away at the waste to find a machine. But what if we've been doing it wrong? Today, we are moving from carving to growing. This is the story of the self-assembling nanowires, the holy grail of nanotechnology.
You know, when you think about it, for pretty much all of human history, we've built things in the exact same way. We're carvers. We take a big hunk of something, wood, stone, silicon, and we chip away everything that's not the thing we want. But nature has a completely different playbook. And honestly, it's way more elegant.
All right, so let's really break this down, because it's a huge difference. On one side, you have what we call top-down manufacturing. This is our world, right? It's the sculptor with a block of marble. It's a factory etching a computer chip from a slab of silicon. You're always subtracting. But then you look at nature, and it's all bottom-up. A tree isn't carved out of a forest. No way. It grows, assembling itself atom by atom, following its own internal genetic code. It's all about adding, building incredible complexity from the simplest little parts.
And that right there is what this is all about. We are right now on the absolute verge of a manufacturing revolution, one where we learn to build our technology the same way life does, by growing it. This is the story of self-assembling nanowires, and I promise you, it's going to change, well, pretty much everything. So, a new way to build. Let's talk about the prophecy and the pioneers. Because this kind of incredible leap doesn't just appear out of nowhere, it actually began decades ago with a few really brilliant minds who just dared to ask a completely radical question.
I mean, seriously, think about this timeline. For thousands of years, since the Bronze Age, we have been carvers. Our entire technological history is built on that top-down idea. But then, bam, 1959, something happens. A lecture is given that plants the seed for a totally new way of thinking. And that one moment set us on a path to where we are today, at the very dawn of self-assembly.
And that spark? It came from the legendary Nobel laureate Richard Feynman. In this now famous lecture, he basically threw down a challenge to the entire scientific world. He said, there's plenty of room at the bottom. What he was asking was, why can't we build things by putting individual atoms exactly where we want them? He imagined writing the entire Encyclopedia Britannica on the head of a pin. Now, that sounded like pure science fiction back then, but what he really did was define the ultimate destination for nanotechnology.
Okay, so great idea, but how on earth do you control something you can't even see? For decades, Feynman's vision was just this beautiful, impossible dream. The real breakthrough came when these pioneers realized the answer wasn't to push atoms around with tiny little tweezers. The secret was to program them. You had George Whitesides at Harvard, who first showed that molecules could actually organize themselves. Then Nadrian Seeman at NYU had this absolutely genius idea to use DNA, life's own programming language, as a kind of microscopic scaffolding. People call it DNA origami. And then you have Chad Mirkin at Northwestern, who created what are essentially DNA glues to stick nanoparticles together. It's literally like biological Legos, with unbelievable precision.
All right, so the pioneers laid all the groundwork. Now let's get into the nitty-gritty, the secret of self-connection. How in the world does a wire literally grow itself out of a chemical soup? The answer is, well, it's just so elegant, it's almost hard to believe.
The whole magic trick hinges on one core principle: molecular recognition. And this isn't something we invented. Nature uses it for everything. The best way to think about it is like a lock and a key. You have one specific key that will only ever fit into one specific lock. That's it. Well, scientists can now design molecules to do the same thing. They give them chemical properties that make them attracted only to their one perfect partner. You can throw them into a chaotic mix of other stuff, and they'll just ignore everything else until they find their match, and click, they connect.
So how do you use that lock and key idea to actually build a wire? Here's the recipe. First, you create a template, a blueprint, using a strand of DNA with a specific code. Next, you get your bricks ready. Let's say they're tiny gold atoms, and you coat them with the chemical that is the key to the DNA's lock, and then you just mix it all together in a beaker. And this is where you just step back and watch. There are no tiny robots, no lasers. Chemistry just takes over. Those gold atoms are irresistibly drawn to their specific spots on the DNA, clicking into place one by one, and a perfect wire literally grows itself. And what you get at the end is just incredible. A flawless electrical connection. A conductive bridge that is thousands of times thinner than a single human hair. The level of precision is just staggering. It's something we could never, ever achieve by carving. So,
Okay, that's a really cool science experiment. We can grow a tiny wire. Why does this matter? What's the real-world impact? Well, being able to build with this level of precision doesn't just improve things, it unlocks entirely new possibilities that could completely redefine computing, energy, and medicine as we know them.
And it's really these three big areas, computing, energy, and medicine, where we're going to see the most jaw-dropping changes. So let's take a look at what this could really mean for each one.
Let's start with computing. For decades, we've lived by Moore's law. Chips get smaller, faster, more powerful. But we are hitting a hard physical wall. The lasers we use to etch circuits can only get so precise. Self-assembly, it blows right past that limit. By growing circuits from the bottom up, we could potentially pack trillions, not billions, I'm talking trillions, of transistors onto a single chip. The leap in computing power is almost impossible to wrap your head around.
Okay, now energy. I want you to picture this. Instead of a flat, smooth solar panel, imagine a microscopic forest of tiny nanowires all standing straight up. Because they have this 3D structure, they are absolutely amazing at trapping light. See, a flat panel works best when the sun is right overhead. But these nanowire forests, they can grab photons coming from any angle, all day long. The potential here is huge. We're talking about maybe doubling the efficiency of solar cells.
And then there's medicine, and this is where it really gets personal. The amazing thing about these nanowires is they're built on the same tiny scale as life itself, things like proteins and viruses. So you can create a biosensor from a single nanowire that is so unbelievably sensitive, it can detect the unique electrical signature of a single cancer cell the moment it makes contact. It's literally like having a diagnostic lab on a chip, operating from inside your body.
Now, after hearing about all this incredible, world-changing potential, it's only fair to ask the big question. We've got to talk about the hurdles on the nanoscale, the big three challenges that stand in the way. Right? If this stuff is so amazing, why isn't it in your phone right now? Why isn't every solar panel made this way? Well, it turns out that going from a perfectly controlled experiment in a lab to mass-producing billions of these things is a gigantic leap. And right now there are some pretty major hurdles to clear. It really boils down to this. Carving gives you control. Growing relies on chemistry. And chemistry, well, it can be a little chaotic. First, reliability. In a circuit with billions of connections, if just one atom misfires and goes to the wrong spot, the entire thing could fail. Then you've got scalability. Making one perfect nanowire is a triumph. Making billions of them all perfect for manufacturing, that is a whole other ballgame. And finally, error correction. How do you debug a process that's governed by the random chaos of chemistry?
So, yes, the future is grown. It's a whole new philosophy for building. And look, researchers are working on these challenges every single day. But what's so exciting is that overcoming them isn't just about making a new gadget. It really represents a deep, fundamental shift in how we even think about technology.
This is the big idea right here. For our entire history, we've built things by imposing our will on materials. We cut, we carve, we melt. This new way of thinking is about working with the fundamental laws of chemistry and physics, letting them do the construction for us. We're shifting from being mechanics of technology to being, well, gardeners of technology.
And that really leaves us with this final thought. We are heading toward a future where our most advanced devices aren't made in sterile factories, but are cultivated in labs. A future where our technology is not some cold, carved object, but a grown, living architecture. The holy grail of nanotechnology isn't just about making things smaller, it's about learning to build with the same elegance and efficiency as life itself.